Okay, so today we're going to talk about basic electric circuits. And so we're going to talk about the differences between resistances in series, parallel, and series parallel combinations, multi-loop circuits, Kirchhoff's rules, RC circuits, ammeters and voltmeters, and household circuits and electrical safety. So 18.1 talks about resistances in a series versus parallel, and then the combination of series parallel combinations. Resistors in series have the same current. So here we have this resistor, which is connected to resistor number 2 and resistor number 3. And so the current does not change when it is wired in a series. So if we were to sum the total of these resistors, the total resistance across the circuit would just be R sub S is equal to R sub 1 plus R sub 2 plus R sub 3. And notice that the voltage does not change. So the voltage here would just be the current times the resistor from here to here. And well, I guess let me rephrase that. The voltage can change depending on what the resistor is. So the voltage is equal to the current times I. The voltage here is the current times, the resistor times R sub 1, and V2 is equal to I R2, and V sub 3 is equal to I times R sub 3. Okay, and so that's how it would look if they were in the series, because the current's the same. And so when we try to find the sum of all the voltages across a series, each resistor equals the battery voltage, and some algebra gives you that the summation is just basically equal to the adding up of the individual resistors in series. So when resistors are in parallel, instead of having them all having the same current, the thing that changes is that they'll all have the same voltage. And again, we need to remember that the relationship between voltage, current, and resistance is that voltage is equal to I times R, which is the current times the resistance. And so when we look at the schematic here, we have a voltage that's coming across, and that has a corresponding current, and then that current gets divvied up when it comes across the parallel circuit. And so the total current then is equal to the sum of the individual currents. So this current gets split in 3 when it enters the parallel. Now the voltage will remain the same, and then the resistors will correspond here. So to find the overall resistance of a parallel circuit, we would use this formula here, formula B, which is 1 over the sum total of the resistance in parallel is equal to 1 over R sub 1 plus 1 over R sub 2 plus 1 over R sub 3. So then the total current of the sum of currents the total current is equal to the sum of currents through each resistor. After some algebra, we find the inverse of the equivalent resistance. And so there's this formula here is how we find the total resistance. Now, when we go to do some math problems with this, we would make these calculations, but remember that the resistance across the parallel circuit is reciprocated. So whatever our number is, we have to reciprocate at the end. So that's important. So the equivalent resistance of resistors in a series is always greater than any individual resistant in the series. And then again, the equivalent resistance of resistors in parallel is always less than any individual resistance in the array because of those mathematical relationships. So for combinations of circuits, we simplify piece by piece. So for A, the current leaves here, and we have R sub 1, which is our first resistor. And then if we go through, we have a couple of parallel circuits, and then we also have within this circuit, we have some more parallel circuits, and then we have another resistor here that's in series with this parallel series. So step A is what we have. Step B, we begin to simplify. In other words, we're going to find the total resistance of this parallel circuit, and we're going to plug that in series, and then we're going to combine these two resistances and think of it as one resistance. Then in the next step, what we're going to do is we're going to combine the resistance of this and this because those are in parallel, and then we can lastly take this resistor and the total resistance here and think of it as the total resistance. So when we go to make calculations with regards to the entire circuit, we take the individual parallel circuits and try to add those up first. It's just a little more convenient. And then once we get all the parallel circuits added together, then we can just add them in series, and that gives us a total sum of our resistance. So here, our first resistor is 6 ohms, this resistor is 4 ohms, and we have a 6 ohms, then a 2 ohm, and a 2.5. After we do some math, the sum of the 6 and 2 in parallel ends up becoming 1.5. And then when we reciprocate it, it ends up becoming, then we have 1.5 and we add that to the 2.5. So these two here become 4. Then we have to add 4 and 4 here, but it's parallel, so it's this formula, so then that becomes 2. And then when we add in a series, we just simply add the resistance, so 6 plus 2 is 8. So the total resistance across the circuit is 8 ohms, but it's derived from 6 and 4 and 6 and 2 and 2.5. So many circuits are not pure series or parallel combinations. More sophisticated tools are necessary to analyze them. Basically, where we run into a little issue is that the current, when you run a parallel circuit, your current gets divided or split up 3 ways, and that has an impact on not only the voltage but the resistance as well. And then the current gets reunited at the other end of a parallel series. So then Kirchhoff's first rule is the conjunction rule, and basically the sum of all currents entering into a junction must equal the sum of all currents leaving a junction, giving the incoming current a positive sign and the outgoing a negative sign. We'll use that in some of our homework. So Kirchhoff's second rule is the loop rule. When we have a loop, if the voltage is greater than 0, we go this way. If the voltage is less than 0, then we go this way, based on this being the positive terminal and this being the negative terminal. The sum of the potential differences around a closed loop is 0 always. Then lastly, the sign conventions for transversing batteries and resistors are at the left. So in this particular case, when the voltage is less than 0, we go this way, with the current going this way across the resistor. And then if the voltage is greater than 0, then we end up going this way. So when we talk about multi-loop circuits and Kirchhoff's rules, we first assign directional currents to each branch of the circuit. We identify enough loops so that every branch is in a loop. 3, we apply the junction rule, keeping independent equations, and then we apply the loop rule. And you should have as many equations as there are different circuits. So we'll take a look at that in our homework. So for RC circuits, an RC circuit can be used to charge a capacitor through a resistor. And so an RC circuit is just a resistor capacitor circuit. So when we look at step A, this is an open switch. When we close the switch, the current will begin to flow. It goes through a resistor. That has an impact on the voltage and the current because of the relationship between the voltage is equal to the product of the current and the resistance. And so then as it comes into the capacitor will begin to charge. And then what we see at step 3, the capacitor will charge it could store the entire voltage, which means that the current will cease to flow. So the current over here will become 0. In other words, the capacitor kind of stops, can stop the current depending on what you're doing. Okay? So when the switch in an RC circuit is closed, the current has a maximum value. All the voltage is across the resistor, and the voltage across the capacitor is 0. As the charge builds up, the current decreases and the capacitor voltage increases. And so basically what we're looking at is this voltage of the battery gets released through a current over this way. The capacitor can store that charge. Once it stores that charge, the potential to some degree is transferred from the battery to the capacitor. So then the voltage as a function of time, V sub C is equal to V naught times the quantity 1 minus E raised to the negative T divided by RC. And so current as a function of time, in other words, if we want to measure the change in that current, the final current would be equal to the initial current times E raised to the negative T divided by RC. Now the quantity RC has the dimensions of time and is called the time constant, or tau is equal to RC. So a charged capacitor may be discharged through a resistor in the case no battery is needed. So a capacitor can kind of work like a battery, and a battery is kind of like a capacitor when you think about it. But when you have an open circuit that closes, you can, or when you can have a, if the capacitor is charged, it can be discharged through a resistor, and if that's the case, you really don't need a battery, is what I'm trying to say. And so then the voltage, based on the relationship V equals IR and this previous equation here, if we solve for V and plug in the R's, what we end up is that the voltage across a capacitor is equal to the voltage, the original voltage, or V naught, times T minus T divided by RC, or V naught E raised to the negative T divided by tau. Okay, so ammeters and voltmeters, basically the deflection of a galvanometer is proportional to the current. Electric current can produce a magnetic field and have an impact on a magnet, and consequently magnetic field can actually produce a current. And so to create an ammeter to measure current, what we would do is we would connect a galvanometer to a resistor in parallel, and we would do this in such a way so as not to change the existing current significantly. Its resistance should be as small as possible, which is why we have the shunt resistor in parallel with the galvanometer and another resistor there, and then a third resistor on the end. And the overall circuit will look like this. And then lastly, the voltmeter is very similar. A voltmeter kind of works in a similar fashion, except we add an additional resistor here, and then the change in current would reflect our change in potential. So this little portion right here is the actual voltmeter. So a voltmeter measures voltage. In order to do this, it must be connected in parallel across the voltage to be measured so as not to change the existing voltage significantly. Its resistance should be as large as possible. And that's all based on V equals IR. So then the multi-range meters, which is what I use a lot in class, must have a selection of shunt and multiple resistors to optimize the measurement of currents and voltages at different magnitudes. So a multimeter will have a switch and the corresponding circuits for measuring voltage here and measuring current here. And then their resistors, those change based on the number of volts that I want to measure and stuff. So how does this relate to our household? Well, household circuits and electrical safety, basically everything that's plugged into our house, it has a ground in it, so household wiring wiring is done in parallel and protected by circuit breakers. And what the circuit breakers do is that if for some reason the current is too large, the circuit breaker will open the circuit and that will stop the flow of current. So if there is a short in the refrigerator, it will draw more current because the resistance is low. If that current gets too high, we don't want that, and so the circuit breaker will pop. Basically, the way that they work, this is an old one. The newer ones look a little different, but there's a fuse strip and the current flows through the fuse strip. Fuses are designed so that the fuse strip will melt, and that cuts the circuit if the current exceeds the predetermined value. Fuses are rated for different currents, and the fuse rating should always match the maximum allowable current through the circuit. If the fuse burns out, it must be replaced. And so you can kind of almost see it here, but there's a little piece of metal. If it's rated at 10 amps and you push more than 10 amps through it for a significant amount of time, and I shouldn't even say significant, a very limited amount of time, like a couple of seconds, that little strip of metal will melt, and then the circuit is broken or open. Circuit breakers are on a similar concept, but basically they're in newer homes because it's a newer technology, and it uses a bimetallic strip that opens the circuit if the current becomes too high. If the circuit breaker trips, it can be reset. This is a thermal trip, and basically what happens is that if the current goes through, there's a little bit of resistance between the two metals, and one metal will heat up quicker than the other metal, and what it will do is it will bend. If that bends, what it does is it'll trip a latch, and that breaks the circuit, and that completes the flow of electricity. It's not that big of an issue. You can flip the circuit back and reset the circuit, and that allows the current to flow. Circuit breakers are a little bit better than fuses, because the fuses, once they're blown, you have to buy a new one. There have been rumors of people bypassing fuses by putting like copper pennies in the fuse box and stuff. Circuit breakers are much safer, and you don't have to buy new ones if they trip. So then in order to provide needed protection, the fuse or circuit breaker needs to be on the hot side of the circuit. That's where the high potential is. So electricity doesn't tend to always follows the path of least resistance. We want to break that circuit on the high potential side. If we put it on the low potential side, that's not good, because then we can still be shocked. So the way electricity in your house works is that the current flows this way, and it can go through an electric device. And if we have the circuit breaker on the ground side, the problem is when you break the circuit here, your hand may actually be ground. In other words, if you're standing on the ground, the circuit will complete through you. Every house usually has a metal pipe or a metal wire that goes directly into earth somewhere, somehow. And then every ground in the electrical outlets in your home are somehow wired to that ground. You can, as a human being, be a path to ground, and that's why it's always better to have the circuit breaker up here on the high potential, so that way if this breaks, it protects your hand and you. So, however, even on the hot side, the fuse or breaker may not protect the circuit. So if an internal wire touches the conductive casing of a tool or appliance, you can still get shocked. This can be avoided by using a dedicated ground line. You can tell which devices have such a thing, which is a 3-prong plug-in. So a dedicated ground line is like a secondary ground. So even if the circuit breaker breaks, you're still protected. The device can still discharge that electrical flow. So in other words, if a current, if we go back to this slide, if a current comes through here and is in the device, then the circuit breaker breaks. There still may be a charge or some electricity in the device, and it may still go through you to find ground. However, on a 3-prong plug, what happens is you have a separate dedicated ground which provides an additional path for that electricity to flow to. So the resistance in a series is just the sum of all the resistances. However, inverse of the equivalent resistance of resistors in a parallel. So we use this formula here for parallel and these formulas here for series. We have some theorems. The junction theorem is that the algebraic sum of the currents entering to a junction is 0. The loop theorem, an algebraic sum of the voltages drops around a loop is 0. And the time constant for an RC circuit is tau, which is R times C. An ammeter measures current and should have small resistance, while the voltmeter measures voltage and should have a high resistance.